All right, ready to dive deep again. This time we're taking on data systems with designing data-intensive applications. You guys sent this one in, so I know you're ready for some serious software engineering talk.
Yeah, this book is like the go-to guide for anyone building applications these days. In our data-driven world and all.
Totally. I was just skimming through it, and one thing that really struck me was how the author, Martin Kleppmann, points out the complexity behind even the simplest things we do online, stuff we never even think about.
It's true, right? Like we hit like on a post or search for something online, but behind the scenes, there's this whole world of complex systems making it all work.
It's crazy when you really stop and think about it. So how does Kleppmann break down this complex world for us?
He starts with, well, he emphasizes these three pillars of good application design: reliability, scalability, and maintainability. Those are the kind of the foundation for any data-intensive application that works well.
Okay, so let's unpack those a bit. Reliability, I'm guessing that means like the system does what it's supposed to be without crashing or, giving you errors all the time.
Exactly. It's about consistency, too. It's not just working sometimes. It's like that reliable friend that always shows up when you need them.
Got it. What about scalability? Is that about handling like those times when everyone's trying to use the app at the same time, like those late night surges?
That's a big part of it. It's the ability of the system to handle growth, without falling apart. Think of a popular social media platform. They need to handle millions of users all at once. If the system can't scale, things crash and slow down. No one wants that.
Right, that makes total sense. And then there's maintainability, right? Where does that fit in?
Maintainability. Well, that's all about making life easier for the developers and the people who keep the system running. Think of it like a well-organized kitchen. Everything's easy to find, easy to fix when it breaks. It's about having clear code, good documentation, all that.
Makes sense. No one wants a messy kitchen or a messy code base. But let's get back to the data itself, right? We're talking about data-intensive applications. How does the book talk about how that data is organized and stored?
One of the first things Kleppmann gets into is choosing between relational and document data models. That's a really fundamental decision. It really shapes how you structure your data, how you query it, the whole thing.
Can you give us a quick overview of those two? I feel like I've heard of them before, but I'm a little fuzzy on the details.
Sure. So relational databases are kind of like spreadsheets on steroids. You've got tables with rows and columns, and you have these strict rules, schemas about what kind of data can go in each column.
Okay, so very structured with those predefined relationships between different pieces of data.
Exactly. And that structure can be a good thing, especially when you need that data consistency. Like in an e-commerce platform, you need to make sure orders are linked to the right customers and the right products.
Right, you don't want things getting mixed up. So where do document databases come in?
Document databases are more flexible. They store data in documents which are, well, basically self-contained units of information, often in something called JSON format. Imagine them like digital filing cabinets where you can put all sorts of related information together in one spot.
So it's more freeform.
Exactly, and that flexibility can be really useful for applications that are changing quickly, or when you're working with data that doesn't fit neatly into those tables. Think of like social media. People have profiles with all sorts of different information.
So it sounds like choosing the right data model really depends on what the application needs to do. But whatever you choose, you still need a way to get to that data, right? To find what you're looking for.
Absolutely, and that's where indexing comes in. Imagine a library with millions of books but no card catalog, right? It'd be a nightmare to find anything. Indexes are like those card catalogs for your database. You can find the data you need quickly without scanning through every single record.
Okay, that analogy makes sense. But I'm guessing there's not just one type of index, right? There must be pros and cons to each one.
Right again? The book talks about all sorts of different indexing techniques like hash indexes, B-trees, essence tables. Each has its trade-offs when it comes to performance, how much storage space they use, and the types of queries they work best for.
Sounds like there's a bit of an art to choosing the right one.
It is, and it brings us back to those trade-offs we were talking about earlier. You have to balance things. Do you want speed over storage space? Do you need to optimize for reads or for writes? Lots to think about.
It's like a constant balancing act. So many things to juggle. Speaking of juggling, one thing I found pretty mind-boggling was the whole concept of replication. How does Kleppmann approach that one?
Well, he starts by talking about why replication is so important for both reliability and scalability. Remember those late-night surges we talked about? Well, replication helps you deal with that by spreading the work across multiple machines.
So if one machine gets overloaded, the others can pick up the slack. But I imagine managing all those copies of the data can get pretty complicated.
Oh, it definitely can. One of the biggest challenges is something called replication lag. That's the delay between when data is written to the main copy and when it's copied to those replicas.
And I'm guessing that lag can cause some serious
Oh,
problems.
yeah, for sure. Imagine you're trying to buy something online and the site says it's in stock, but then you get an email later saying, oops, actually it was sold out. That could be because of replication lag. The system you were looking at hadn't caught up to the latest information.
Ugh, I've totally had that happen. Super frustrating. So how do you minimize that lag? Or even get rid of it completely?
Well, there are different methods, each with their own trade-offs. There's single-leader replication, where one machine is in charge, and multi-leader replication, where several machines can accept writes. There's even leaderless replication, where any machine can handle both reads and writes.
Wow, so many options. It's like trying to pick the right coffee blend. Each one has its own flavor profile.
Exactly. And like with coffee, the best choice depends on your taste, or in this case, the needs of the application. A simple blog might be fine with single leader, but a big global e-commerce site might need multi-leader for all those updates from different parts of the world.
Okay, so no one-size-fits-all solutions. You really have to think carefully about those trade-offs. And I'm seeing a theme here, whether it's the data model, the indexing, the replication. It's all about making smart choices based on what the application needs.
Absolutely. And that's what makes designing data-intensive applications so challenging, but also so interesting.
Well, I'm definitely feeling a little overwhelmed, but in a good way. It's like I'm starting to see all this hidden complexity behind those everyday actions we take online. Makes you appreciate the work that goes into it.
Totally.
I'm excited to learn more. So what else is coming up on our deep dive? What other fascinating concepts does Kleppmann have in store of us? All right, so we've talked about reliability, scalability, maintainability, data models, indexing, and even touched on replication. It's a lot. My brain's doing a data dump over here.
Yeah, there's a lot to take in, but you're doing great. It's a foundational text, so it's going to make us think.
Well, I'm ready for more thinking. What's next on our deep dive itinerary?
Let's talk about partitioning. That's a big one for building applications that can handle huge amounts of data and lots of users, applications that can really scale.
Okay, partitioning, I vaguely remember hearing about it, but can you refresh my memory?
Imagine you have a library, right, with millions of books, but no organization, just books everywhere. Finding anything would be a nightmare. Partitioning is like creating those sections in the library, dividing the books into chunks based on some criteria, like genre, author, whatever makes sense.
So it's about breaking a big data set into smaller, easier to manage pieces.
Exactly. And in data systems, those pieces are spread across multiple machines. That way you can process and query the data much more efficiently.
Right, because trying to handle everything on one machine would be like trying to fit all those library books onto one shelf. Not going to happen. But how do you decide how to partition the data? I mean, there must be lots of ways to divide it up.
There are. The book talks about different schemes, each with, pros and cons. One common one is key range partitioning. You basically set boundaries based on the value of a specific key. So like on an e-commerce site, you might partition orders based on the order date. All orders from a specific day go together.
Makes sense, like organizing the library by publication year. But what if certain key ranges are accessed way more than others? Wouldn't that cause bottlenecks?
It could. That's the downside of key range partitioning. If one particular range gets really popular, it can overload the machine that's handling that partition. Think about a social media site where everyone's trying to see a celebrity's profile. Everyone's hitting the same partition.
Oh, right, like a digital stampede to one section of the library. So how do you avoid those hotspots?
Hash partitioning. Instead of using the key's value, you use a hash function to distribute the data more randomly. It's like assigning books to shelves using a random number generator. It spreads things out more evenly.
So hash partitioning is the great equalizer, preventing those big bursts of activity from overwhelming one spot. But doesn't hashing make it harder to retrieve data based on those key ranges?
It does. Hashing kind of scrambles the order of the keys, so ranged queries become less efficient. Another trade-off, the book also mentions hybrid approaches, combining key range and hash partitioning to try and get the best of both worlds.
Like having a multi-level system in the library. You can browse by genre or author, but you also have that random scattering to keep things from getting too crowded in any one spot.
That's a good way to think about it. And the takeaway is, choosing the right partitioning scheme is a really important design decision. It affects performance, scalability, the whole nine yards.
Well, I'm really seeing why this book is so popular with software engineers. It's like full of these practical tips you wouldn't think about unless you've been there, done that. But let's move on to another key concept. Transactions. Why are they so important? Give us a quick overview.
Transactions are all about data integrity, making sure that a series of operations are treated as one unit. Think of it like transferring money between bank accounts. You want to make sure either the whole transfer happens or nothing happens.
Right, you don't want money disappearing or magically duplicating. But how do transactions actually, work in data systems?
The book goes deep on what are called the ACE-ID properties of transactions: atomicity, consistency, isolation, and durability. Those properties are what guarantee that transactions are reliable and predictable, even when lots of things are happening at the same time or if there are, failures.
Okay, let's break down those assay properties. Atomicity, is that the all or nothing thing we talked about with the bank transfer?
Exactly. It means a transaction is a single unit. All operations succeed or none of them do. No halfway.
So like a light switch, it's either on or off, no in between. What are we consistency?
Consistency is about making sure the transaction takes the database from one valid state to another. No corrupted data, no breaking the rules. Think about a database for a library, right? Consistency would make sure you can't check out a book that's already checked out.
Makes sense, keeping the data sensible. So what about isolation?
Isolation is about how different transactions happening at the same time interact with each other. Imagine several people trying to update the same library record at once. Isolation keeps those updates from messing with each other, makes sure each transaction sees a consistent view of the data.
Like separate workspaces for each person, no one stepping on anyone's toes. And finally, durability. I'm guessing that's about making sure the changes are, permanent.
You got it. Durability means that once a transaction is done, the changes are saved and won't get lost, even if the system crashes. It's like writing those library updates in, I don't know, indelible ink or something.
So the ACID properties are like, the guardians of data integrity, keeping our data safe from all sorts of threats. But are there different levels of isolation? How strictly do you need to separate those concurrent transactions?
Good question. And yeah, the book talks about different isolation levels, each with its own trade-offs. The strongest one is serializability. It makes transactions act like they're happening one at a time, totally separate from each other.
Sounds like the safest option, but probably not the fastest.
You're right, serializability can slow things down, especially in systems with lots of transactions. So there are other levels like read committed and snapshot isolation. They offer weaker guarantees, but can be faster.
Again, it's about finding that balance, right, between data integrity and performance. It's all starting to click now, but I feel like we're about to enter a whole new world of complexity. Distributed systems, are we going there next?
You read my mind. Get ready to explore the wild west of distributed systems, where things can get, well, a bit unpredictable.
Oh boy, can't wait, bring on the chaos. Okay, so we've gone through data models and indexing and replication. We even touched on those ACID properties of transactions. I'm starting to feel like, I don't know, a database expert or something.
You're getting there. But get ready because now we're going into distributed systems. It's a whole different ballgame.
Ooh, sounds exciting. But seriously, what makes distributed systems so different from what we've talked about so far?
Well, it's not just one machine anymore. You've got multiple machines, often in different locations, all working together.
Like a team of computers, huh? Sounds efficient, but I bet it's also a lot more complex.
Oh, for sure. One of the biggest challenges is that networks aren't perfectly reliable. Connections can be spotty, messages can get lost, machines crash. It happens.
Yeah, it's like trying to talk to someone over a bad phone connection. You're never quite sure if they heard you, right? So how do you build systems that can handle that kind of unpredictability?
That's where fault tolerance comes in. You design the system so that it can keep working even if some parts of it fail. It's like having a backup generator, just in case the power goes out.
So it's all about redundancy, but I'm guessing there are different levels of fault tolerance, right? Like, how many backup generators do you actually need?
It's not just about throwing more hardware at the problem, you're right. The book talks about different strategies for fault tolerance. Replication is one, like we talked about earlier. And there are techniques like timeouts and resize, for when a machine isn't responding.
So a mix of smart design and clever engineering to keep things running smoothly. I'm also curious about this whole concept of consensus. Why is that so important in a distributed system?
Consensus is about getting all those machines to agree on something, a shared state or a decision, even if some of them are out of contact or having problems. Imagine, like, a group of hikers trying to decide which path to take. They need to reach a consensus, even if some of them are temporarily out of radio range.
Right. Otherwise, they'll all end up going in different directions, and, well, that wouldn't be good. But how do you get consensus in a system where messages can be delayed or lost and machines can crash?
That's where consensus algorithms come in. The book talks about some of them. Paxos and Raft are a couple of examples. They're designed to handle those failures to make sure all the machines eventually agree, even if there are, network issues and things like that.
So it's like having a designated leader to keep everyone on the same page. But I bet those algorithms are pretty complex, huh?
They can be, but the book does a good job of explaining the basics. It's all about multiple rounds of voting and message exchanges, lots of careful handling of, those tricky edge cases to make sure everyone eventually agrees.
Sounds like a complicated dance, keeping all those machines in sync. But let's talk about consistency. That's another big one, right? How does it relate to consensus?
Consistency is about making sure all the machines have the same view of the data, even if there are failures. And yeah, consensus is often a big part of achieving consistency.
So it's like making sure all the hikers have the same map, even if some of them have been working with an outdated version. But I'm guessing there are different levels of consistency too, right? Just like with those isolation levels for transactions?
Yep, the book talks about different consistency models, each with its own trade-offs. Linearizability is one of the strongest. It makes the system act like there's only one copy of the data and everything happens in a strict order.
So it's like having one official map that everyone always refers to. No outdated versions floating around. But that level of consistency must be tough to maintain.
It can be, yeah. It requires a lot of coordination between all the machines, which can slow things down. So the book also talks about weaker consistency models, like eventual consistency. You allow for some temporary inconsistencies, but eventually everything catches up and becomes consistent.
Like letting the hikers work with their own local maps, but knowing that eventually they'll all sync up and merge their changes. And it's all about choosing the right consistency model for the situation.
Right. A financial app might need that strong consistency to make sure account balances are always accurate. But a social media site might be okay with eventual consistency for something like, a news feed.
So much to think about when it comes to distributed systems. Fault tolerance, consensus, consistency. Like navigating a minefield of, tricky trade-offs. But I'm curious, what about the future of data systems? Where does Kleppmann see things going?
The book argues for a more, how do I put it, a more unbundled approach, moving away from those big monolithic databases and towards more specialized systems, each one optimized for a particular job.
So like having a team of specialists instead of one general practitioner.
Exactly. And then there's this idea of data flow. Imagine data changes flowing through the system like a river, with different systems acting as, dams and reservoirs and tributaries, each one processing the data in its own way.
Like a complex network of pipes and channels making sure the data gets where it needs to go. But I bet that approach has its own set of challenges too, right?
Definitely. One of the big ones is making sure everything stays correct and consistent when you have all these different parts working asynchronously. The book talks about strategies for dealing with that, like clear interfaces, reliable messaging systems, and good data governance practices.
So it's about making sure all the pieces work together smoothly, even though they're operating independently. Well, this has been quite a journey. I've learned so much about how data systems work and the challenges of designing them to be reliable, scalable, and, maintainable.
It's been great diving deep with you. And remember, we've just scratched the surface. The book has a lot more to offer anyone who really wants to master this stuff.
Absolutely. And for you listening, the key takeaway is that understanding these fundamentals can help you make better decisions, design better systems, and ultimately build better applications. So until next time, keep exploring, keep learning, and keep diving deep.